Alright, so we're going to work on a few problems today on universal gravitation. This is on page 3 in your packet. So on the left side of page 3, numbers 1 through 9, it's all conceptual stuff. I'm not really going to spend the time going over this. This could be found in the notes. What I am going to spend time on is the calculations on the right-hand side of the page. So numbers 10 through 13. Okay, so our first calculation, actually our equation that we're going to be using for all of these is my universal gravitation equation. And this one should be written on your notes already. I'm going to go ahead and write it up here at the top. It is the force of gravity is equal to big G, which is a universal gravitation constant right here, 6.67 times 10 to the negative 11, times two masses, it's mass 1, mass 2, all divided by the distance between those two masses squared. Okay, so when I'm looking at my first problem here, number 10, it wants me to calculate the Earth's mass using the fact that 1 kilogram mass weighs 9.8 newtons on the Earth's surface, and the Earth's radius is 6.4 times 10 to the 6. Okay, so we're going to be dealing with some very large numbers, or maybe even some very small numbers. So scientific notation is going to be very important. I like to write all my numbers in scientific notation using the E. So this gravitation constant with the E would look like this: 6.67 E negative 11. So the E takes the place of the times 10 and the caret that you would normally have to write or type into your calculator. Plus, you don't need to use parentheses to solve this problem. Okay, so looking back at my first problem, it says calculate the Earth's mass. So right here, right off the bat, I want to know the mass of the Earth. Okay, now it says the fact that a 1 kilogram mass weighs 9.8 newtons on Earth. So here is another mass, my second mass. Oops. And it weighs 9.8 newtons. So its gravitational force is 9.8. This is Fg. Okay, and the Earth's radius is 6.4 times 10 to the 6. So this is the distance from the center of the Earth to the top of the Earth. This is D. Okay, so I have two M's, D and Fg. Now I'm going to plug them into my equation just like it's written. So my first order of business is writing in the Fg. So Fg was 9.8. So if I rewrite this, I get 9.8 equals big G, which is 6.67 E negative 11, times my first mass, which is 1 kilogram, and my second mass, which is unknown right now, is the mass of the Earth. I'm just going to leave it as an M. And all of that is divided by the distance, which is 6.4 times 10 to the 6 squared. Okay, so the easiest thing to do would be to cross multiply. So you can see here, I want to solve for M. It's in the numerator. I want to get M by itself. So my first order of business would be to cross multiply. So I need a fraction on the left, and I'm going to cross the 9.8 with a 6.4 times 10 to the 6 squared, and then the 1 times everything that's up here on the top. And it looks like a lot, but it's really not once we get going. Okay? So when I multiply the 6.4e6 squared times 9.8, when I type that into the calculator, I get 4.01e14 equals, and when I cross multiply the 1 times everything that's on here, well, 6.67e times negative 11 times 1 is just 6.67e negative 11, and then times m. So I don't know m yet. So I'm going to rewrite it just like it is here. So 6.67e negative 11 times m. So m, you can see, is being multiplied by 6.67 e negative 11. So the opposite of multiply is to divide, and I need to divide that on both sides. So 6.67 e negative 11 here, and 6.67 e negative 11 here. So these will cancel out. And when I divide these two here on the left, I get m. And after I type these into my calculator, my m turns out to be 6.02 times 10 to the 24th kilograms. This is the mass of the Earth that we have calculated. Okay, the next one on here. Calculate the force of gravity between a newborn baby with a mass of 4 kilograms and the planet Mars, a mass of 6.4 times 10 to the 23rd. When Mars is at its closest to the Earth, a distance of 8.8 times 10 to the 10th. Okay, so I'm looking at this problem, and I see I want to calculate the force of gravity. So I need to solve for Fg. I also know the mass of the newborn baby is 4 kilograms. That's my first m. The mass of Mars, 6.4 times 10 to the 23rd. That's my second m. And the distance between the two is 8 times 10 to the 10th. Okay, so this is D, this is M, and I want to solve for Fg. Fg is my unknown. Okay, so same equation as above. My force of gravity now is unknown, and that's equal to big G, which is 6.67 times 10 to the negative 11, times my first mass, which is the mass of the baby, times my second mass, which is the mass of Mars, which was 6.4 times 10 to the 23rd, all divided by the distance, which is 8 e 10 squared. Now this is a little bit easier. There's no rearranging because I'm solving for Fg. This equation is already rearranged to solve for Fg. It just comes down to typing this into the calculator. Okay, so after it's all said and done, when I type this into the calculator, I get a nice answer of 2.67, and I'm rounding, 2.67 times 10 to the negative 8 newtons. So the force of that baby, between the baby and Mars, is 2.67 times 10 to the negative 8. Okay, moving on. Number 12. Calculate the force of gravity between a newborn baby. So again with this baby's popular. The baby has a mass of 4, and between the obstetrician, so the baby's doctor, with a mass of 75, and those two are 0.3 meters away. Okay, I want to calculate the force of gravity. So here I am solving for Fg. Fg is unknown. Okay, 0.3 is my distance. Here's the mass of my baby. Here is the mass of the doctor. Okay, so same equation as above. Fg equals big G, which is 6.67. This is a constant, it never changes, times the mass of the baby, which is 4, times the mass of the doctor, which is 75, all divided by the distance between those two, which is 0.3 squared. Okay, again, this problem is already rearranged to solve for Fg. All I need to do is type this into the calculator, and when I do that, I get a force between those two of 2.22, and I'm rounding again to the second decimal, times 10 to the negative 7 newtons. Okay? And my last one. What is the attractive force between a person and their cell phone? If the average distance between them and their pocket is 2 millimeters, and the average mass of a person is 70 kilograms. Okay, so it also gives you a hint here. The mass of a phone is 166 grams. I need to convert the mass to kilograms and then solve. So I need to convert this mass to kilograms. I also need to convert this distance to meters. So let's look at that. So the phone has a mass of 166. Now, I know that there are 1,000 grams in 1 kilogram. So if I'm converting from grams to kilograms, I need to divide 166 by 1,000 to get my mass in kilograms. So this turns 166 divided by 1,000 gives you 0.166 kilograms. This is one of your masses. Okay? The mass of the person is 70 kilograms. So this is your second M. The distance between those two is 2 millimeters. Now, there are also 1,000 millimeters in 1 meter. So to figure out that conversion, I'm going to take 2 and I'm going to divide it by 1,000. So this becomes 0.002 meters. Okay, so this is my distance. So I have D, I have M, I have my second M. I want to know the attractive force, so I'm trying to find FG between those two objects. Okay, so the same equation. Force of gravity is equal to big G, which is 6.67 times 10 to the negative 11 times the first mass, which is the mass of the person, times the second mass, which is the mass of the cell phone, which we converted to 0.166, all divided by the distance, which we also converted to meters as 0.002 squared. Okay, and after I type all this into the calculator, I get a force of gravity between the two objects, the cell phone and the person, of 1.94 times 10 to the negative 4 newtons.